Good morning and welcome to our webinar, Failure Analysis in Electronics, a Physics of Failure Approach, presented by DFR Solutions. We're going to give everybody another 2 or 3 seconds to log on. We'll begin momentarily. All right, hello again and welcome to our webinar on Failure Analysis in Electronics, a Physics of Failure Approach. Your presenter today will be Jim McLeish, the Senior Member of Technical Staff at DFR Solutions. Jim, I believe you have an introduction slide lined up, so I'm going to let you take it from here.
Okay. Good morning or good afternoon to everybody, depending on your current location, and thank you for joining our webinar today. We are DFR Solutions. We're a failure analysis and environmental life test, engineering consulting, and CADE software development firm. And we are all experts in the physics of failure research approach to learning from failures for electrical and electronic technology. We focus on a total approach to quality, reliability, and durability of EE systems, components, materials, as well as test methodologies applied to them and the fabrication and assembly processes. So for us, failure analysis is applied for failure mechanism identification research, and we use this knowledge to develop failure prevention strategies. And as Ed said, I'm Jim McLeish. I'm a senior member of the DFR technical staff, and I'm also the manager of our Michigan office in Rochester Hills, Michigan, outside of Detroit. I've got over 35 years of vehicular, military, and industrial electrical and electronic experience in QRD. I've been working, started out as an electronic module designer and systems developer, got into development, validation, lifecycle management, and before I joined DFR, I was the electrical and electronic reliability manager and a QRD root cause failure analysis technical expert at General Motors. So DFR Solutions, we're located in Beltsville, Maryland, just outside of the Washington Beltway. And you can see here the pictures of our facility and a shot of our failure analysis lab and our chemical analysis lab. And while we're headquartered and have our lab in Beltsville, Maryland, again, near Washington, D.C., we also have offices in Rochester Hills, Michigan, Minneapolis, Minnesota, Austin, Texas, and Binghamton, New York. And we now have representation in people in Europe and Finland, or I should say in Finland and Germany for the European Union. So today we're going to be talking about failure analysis, particularly as it's applied to electronics. And failure analysis is really a subcategory of root cause problem-solving analysis. So it's one of a number of different strategies that can be applied for root cause problem-solving. And failure analysis specifically is applied when there are some kinds of physical remnants of a failed part. And these parts are available for examination and various types of testing. Now, the best practice in failure analysis is not to start with the physical testing, but to actually start by collecting as much information as possible on the history of the failed parts and the kind of situation of how, where, when the failures occurred, or the various types of failures occurred if it's happening to a number of items in your production family. So we also see it useful to know kind of the condition or the status of the part that's failing. Is this a new, perhaps unproven device that's still in development or in testing and failed in some form of qualification or validation test or performance test? Or perhaps it's a proven device that has worked for years in a number of applications and now it's being served and used in a new application or by a new customer and problems are coming up. Or is it a proven device that suddenly started failing in the field that it's been working reliably in for years, which might indicate that you've got some kind of quality spill situation going on in either your assembly or your supply chain processes. Is it an inline failure? Are they coming off your line and all of a sudden you're having some kind of assembly or fabrication problem? Are your OEM equipment customers for their plants returning them because they're dead on arrival? And maybe there's something happening in shipping there. Is it infant mortality at the final end user? So another important issue is, are these failures unique? Only a few parts happening, or is it epidemic? Is it happening all over many, many times? And are the failures perhaps seasonal or maybe regional, where we're seeing different weather trends or usage techniques in different parts of the country or climate? So these are some of the very useful informational items of background info that are very, very valuable sometimes when you're starting a failure analysis. So wherever you got data that you can find and use, it's something you should collect, capture, and keep that along as you proceed to the physical portion of the failure analysis process. So, as I said before, failure analysis is a subcategory of root cause, and it involves systematic examination of failed devices. And you can use this knowledge to maybe fix your current products, and that's, of course, all good and fine. Nobody wants to have unhappy customers or a high warranty cost situation or worse yet, some kind of government regulation oversight. However, the better situation is when you take the knowledge and don't just think about putting a Band-Aid on your current problems, but you try to learn from it and reuse and capture that knowledge on all of your future product development activities, so you make sure that you never repeat the situation that led to this failure condition again. So that's what we try to promote as much as possible. Now, physical failure analysis techniques are primarily associated with physics and material science of mechanical, structural, electrical characteristics of the product, along with the material properties that all of your electrical and electronic devices, circuit boards, housings, whatever are made of. So in other words, we're talking about hardware here. Now, there is another discipline of software failure analysis, which is becoming a very growing subcategory in FA. It involves your computer science and programming skills and forensic software debugging and things of that nature. But we're not going to be covering that in today's webinar. And there's also what's known as forensic engineering, another subcategory of failure analysis that relates to when you're using the techniques to investigate failures or more malfunctions in order to establish facts for some kind of criminal or civil legal action that might be pending. And when you have this, it requires the highest degree of maintenance of your chain of evidence. And you also have to comply with the various rules of evidence that is in the legal jurisdiction that you are working in. So this is also another special subject, and we won't be covering that today. We will be focusing on electrical and electronic hardware items. So effective failure analysis is really an essential core competency for an organization that wants to achieve good product reliability, because there are going to be days when nothing goes right, problems pop up. Unfortunately, every product does not launch flawlessly, and so having the ability to identify the type and source and root cause of your failures so that you can develop an effective corrective action is essential. Otherwise, you risk repeating these kind of outbreaks again and again and again, maybe not in this product, but somewhere else. So it's also important to have a systematic approach to failure analysis. And there are many different types of failure analysis techniques. We're only going to be getting into some of the most popular ones today. This webinar is actually a introduction or a small version of a two-day class that we teach on failure analysis and failure mechanisms. So we can't hit everything in 2 days and 1 hour here, so we're going to be taking a few shortcuts and summarizing some key points. Okay. There we go. So failure analysis best practices involve identifying the failure mode, which we call the way a product fails, or is observed or detected. And then you want to identify the specific failure site of what failed or what occurred. And once you have that, you want to focus on understanding the failure mechanism, the cause of events or phenomena that led to the failure mechanism being initiated and propagated until it turned into a full failure. Now, in a lot of organizations, the terms failure mode and failure mechanisms are used interchangeably. And we don't do that when we are applying a physics of failure approach. We understand that the failure mode is how you observe or detect the problem, and the mechanism is the condition, the chain of events, deterministic causes that led to the failure to occur. And so we want to have all of this in order to determine the true root cause that led to the failure so we can come up with an effective failure prevention strategy. Now, something else to keep in mind is not all failure analysis labs or analysis plans are the same. There are actually some different service levels. And so there is what might be called the basic or highly competitive FA that a number of failure analysis labs practice. And in this case, the failure analysis personnel or laboratory is only going to limit themselves to specific factual reports of physical evaluations of the failed device or remnants that they are provided with. So they will try to identify the failure site for you and provide as much factual information as possible. And then they're going to send that back to you, and it's now up to you to use this information in your root cause analysis methodologies. Or you've got to continue it on, and you've got to collect your historical data, and you've got to decide if you need additional evaluations and things of that nature. So this is where the failure analysis lab is doing, a specific set of basic functions, again, limited to physical evaluations of whatever they're provided. That provides the lowest cost, but there's no correlation to the device history, and usually you don't get a root cause identification. You get what we call a picture with the "it broke here" arrow, like I'm showing on the right side of these slides here. Hey, we found a solder crack at ball A14. Or hey, we found, we decapsulated the IC and we found a electrical overstress where the metallization fused into an open circuit. So they will tell you here is the failure, but not an indication of maybe how that failure can, it'll be classified as something very generic like solder crack or electrical overstress. Now then there's the more comprehensive failure analysis where you kind of get involved more with your failure analysis technical experts, and you provide them some of the background information and guidance on what you think is going on. And they can collaborate with you to develop, instead of just basic physical procedures, a series of physical procedures and evaluations that will hopefully lead us to a root cause. So this is kind of where you work in partnership with the failure analysis lab personnel. Now, the highest level is what we call a physics of failure-based failure analysis activity. And here, the physical evaluations focus on identifying various types of forensic signatures of various types of failure mechanisms that are what resulted in the failure. And this is what we are very, very adept at DFR Solutions because of our years in physics of failure research, identifying and characterizing these failure signatures. And as an example here, this was a vehicle wiring harness that went through a seat, and the consensus was that the wiring harness was being stretched back and forth as the seat was being moved, and there was tensile loading resulting in the shearing of the wires. And when I was brought in, I looked in here and I saw this curl around, and I looked at the wire, each strand individually, with a simple magnifying glass, and I saw this half-moon cut across only half of the cylindrical wire strands. And that told me that what was happening here was the wire was being bent, not pulled. If it was being pulled, it would have been forming like hourglass, narrowing down around the entire circumference of the wire strand, not a sharp cut around half of it like that. So that's what we mean by understanding the various failure signatures for different failure mechanisms, because when you know these things, it empowers you to rapidly go through the failure analysis procedure and select the most effective procedures that are most likely to provide a root cause identification for you. So this winds up requiring staff that has a little bit more expertise, such as what we have at DFR Solutions. Now, we, in the physics of failure vernacular, we identify three general categories of failures. The first one is what we call the overstress failure. And this is when the stresses that are applied to your product or device, and in this case stress can be an electrical or a thermal stress or a mechanical load or a compressive load or a tensile load. It can be vibration, whatever. What it basically means is that the stress of the environment or the usage condition overpowers the strength of the material. And we illustrate this with two bell curves here on a distribution. The blue curve on the bottom is signifying the stress that comes from your environment and usage conditions. The red curve on the top signifies the distribution of the strength of your product or whatever system or device is being attacked. And we all know that there is a bell curve distribution about a mean. Engineers try to understand the mean, and in the mechanical and structural world, they have what they call the design margin or safety factor, where the mean strength has to be X times stronger than the mean stress, because they did not know exactly what the distribution of the stresses are. Because if you get a case where the blue line starts to creep into the area of the weakest parts of the red line, you're going to have some degree of fallout there. So that's why you want to have these distributions as tight as possible around the mean and as much separation as possible. Now, the next one is what we call the approach to how parts age and wear out. And this is really an issue of what we call stress-driven damage accumulation in materials. So I'm going to have an example here of a mechanical structure that is the red box here with the blue box on a couple of triangular mounts, and it's getting a load applied to it. So this could be a table taking the weight of books or a desk set or whatever. And again, loads here could be any kind of physical manifestation, electrical, chemical, thermal, mechanical, whatever. Now, whenever a structure or material is loaded, it is stressed. And that means that the forces, the loads, are going to be distributed throughout the design until it comes into some form of equilibrium with the strength of the design resisting the applied load. But when a device is stressed, it is also strained, which means there is some instantaneous change in the materials or the structure, And this can be coefficient of thermal expansion and contraction under heating and cooling conditions. It can be elastic compression or stretching under mechanical load conditions. It could be a piezoelectric effect, a number of things. So we want to understand this load, stress, strain condition in the various materials we use to make electrical and electronic devices, whether it's an integrated circuit or a resistor or a circuit board. Now, as materials are strained, if they are strained too much, they go into what's called plastic deformation, which means they accumulate a permanent change. If the strain is light, they stay in what's known the elastic range, which means like a rubber band, you pull it out, you let it go, it snaps back to its original position. But with that rubber band, if you take it out too far and let it go, it may not come back 100% to its original condition. And if you take it out to that extreme load again, you're going to get another reduction in its return capabilities. And that is because we are doing molecular damage when we take it out so far that we break molecular bonds inside the material and we start to weaken the device. So this is what we mean by damage, accumulation, or stress-driven aging. Now, eventually, if you keep applying these cycles or continuously loading conditions, you are going to come up with failures that will occur either at a point where you have a stress concentrator, a overall weakness of some sort of the design, or possibly a material or process variation or a defect that put in, instead of a design weakness, a variation-induced weakness. And understanding what are various weaknesses and potentials for variation as materials help us identify where the potential weak links in the design could be, so we know that we need to fortify them a little bit. Now, if we understand all of this reaction, it allows us to be able to predict a mean time to failure for a category of devices under various types of stress conditions. And because we have again been studying our physics of failure, developing forensic signatures, we also understand the kind of distributions about the mean of various types of failures. So we can predict what kind of distributions we will be seeing. And this is a very useful thing, and sometimes this is helpful in failure analysis because we go back and apply these equations to understand, okay, maybe the first failures we're seeing here are the tip of the iceberg, but if other parts continue to age, what could be the fallout rate that we would anticipate seeing in the future if this issue isn't resolved? Now, the third class of generic failures is what we call errors and excessive variation. This correlates to the classical concept of quality. And this is kind of the hardest one to control because there are so many factors, interfaces, people, equipment, materials, your environments, that cause different amounts of weaknesses, errors, or stress levels to be inflicted on the entire design or the design's assembly process. And that will overall act up to give us another form of performance curve. So I got a little diagram here of a pin and hole solder joint, and you can see that this is not a very good soldering process. It puts a lot of air bubble voids in here, which means that this joint is not as strong as it could be. This could be a weak link because the soldering process was not optimized to prevent these air bubble voids from forming. So let's get back to failure analysis techniques now that we set a little bit of basis on what kind of failures we think we should be looking for under various conditions. So there are three primary failure analysis techniques categories. So there is what we call non-destructive evaluations, which are basically inspections and either physical or electrical types of measurements. And these are what we usually start out with because they are the issues that will not cause any problems or risk destroying any evidence by the techniques we call destructive evaluations. This is when we got to cut something open, grind it, slice it, dissolve it, whatever, so we can see inside what might be happening with some kind of internal inspection. We want to take the hidden and reveal it. And we try to delay these as much as possible till we have learned as much as we can from various non-destructive evaluations. And then there's another category of what's called material and or chemical and material property characterizations. Now, usually these are destructive evaluations because you have to form some kind of sample out of the device in order to put it into a specific series of tests to see if the device stands up to expected material properties or electrical performance parameters. So these are the three general classifications that may come to bear in a particular type of failure analysis project, dependent upon what you're analyzing. And again, we always start with non-destructive techniques as much as possible, and you can consider a failure analysis very often to be akin to peeling away a layer of an onion at a time until you get to the core to see what's going on. Another good technique is to always employ your simplest, lowest cost tools first, because you never know, you might get lucky and find it using these quick, low-cost methods rather than having to wait to go to more elaborate and costly procedures. So, we're going to go through and walk you through some of the frequently used failure analysis techniques. Looks like we got a lot of people trying to come in here late. Sorry for these interruptions. Anyways, in the three categories, there is the non-destructive evaluation techniques. There are visual inspections and physical measurements, often using optical microscopy. Various electrical characterizations and tests. There is an ultrasonic acoustic microscope, X-ray microscope, infrared thermal imaging, a rather new technology called Superconducting quantum interference device, or the SQUID microscope for short. And there's also the focus ion beam microscope, which allows you to mill and trench components in order to cut into them in very, very fine locations. Now, we then move into our destructive evaluation techniques. Decapsulation, where you dissolve away the outer protective package or housing of an electronic device so you can directly inspect its core technology or active element. Cross-sectioning, another way where we will cut into a system or device or a circuit board assembly at various depths, possibly a sequence of depths, in order to see what is going on at different planes into the structure. Very often we'll use scanning electron microscope and electrodispersive X-ray. You'll say, why is a microscope destructive? Well, you have to cut up a very small sample of a device and put it in a vacuum chamber. It's not like you can take an entire electronic module or circuit board and put it underneath your lens of your microscope because there's very small chambers that these things will fit in. And then there's X-ray fluorescent analysis, another one. Finally, we have chemical and material characterization methods. So there are various types of mechanical testing, wire bond pole shear test, coefficient of thermal expansion, thermal methods such as differential scanning calorimetry, DMA and TMA thermal mechanical analysis, chemical techniques such as ion chromatography for ionic residues, and Fourier transfer infrared spectroscopy for organic characterization. So I'm going to briefly go through some of these techniques. So we virtually always start out a failure analysis with detailed visual inspection, a non-destructive evaluation process where we very closely look over the device to see if there are any kind of abnormalities going on, damage, defects, discolorations, things of that nature, charring, cracking, something that might indicate that here's where our abnormality is occurring. So you can start with the naked eye and then move up to a magnifying glass and an optical microscope. These can be performed at a very reasonable cost with reasonable costs of equipment. And it is very useful to have a digital camera capability so you can document anything unique that you see or even the lack of a problem for future reference or to include in your failure analysis report. So we're also using these techniques a lot for rapid identification, what is unfortunately becoming a growing concern related to counterfeit parts. This is becoming an increasingly prevalent problem throughout the electronic industry, and a lot of failure analysis labs are spending their time finding out that the reason parts were failed is because it isn't a real part that it pretended to be. It was some kind of knockoff coming out of some back corner of Asia or India or wherever sometime. So when you're doing your optical or visual inspections, lighting conditions are very, very helpful. Different kind of lighting, polarized lighting, UV lighting, infrared, all of these things can bring out different characteristics that you might not see directly in a normal field of vision type condition. And of course, optical microscope, this is where we get a lot of benefits of using lenses and light to magnify things and get a very, very close look at what might be happening or what might be a problem. Now, we also have newer microscopes with fiber optics that allow us to look under these very low-profile BGAs and QFN type packages that are coming out these days. Saves you from having to cut the part apart and look at it, and this is very useful for initial upfront quality inspections as well. So when you're doing your visual inspection, you want to look for any signs of charring, discoloration, or perhaps soldering problems, insufficient solder, poorly positioned solder. You could also be looking for debris, contaminants that are left in your circuit board or maybe got wedged underneath your components. And it's also good to look for any kind of cracking or deformation, like if there was a heat event that twisted and warped something, or you could have also had conformal coatings or solder mask or some of the features that are designed to keep moisture out, cracking and flaking and peeling away, making the design more susceptible to moisture and humidity attack. Electrical characterization is pretty much another essential step. You always want to try and power the device up or read voltages, currents, resistances, wherever possible in order to confirm that the part is actually failing in the condition that it was reported to be in. And it's not unusual to get what's called no trouble founds or no fault founds, where somebody said this part wasn't working in the field or it wasn't working on the line, and they send it up for analysis, and it seems to be working perfectly by the time it gets to the FA lab. So this can be a very challenging situation. You don't know if the initial diagnosis that sent it into failure analysis was wrong, or if maybe, and this is what gets nasty and drives a lot of people up the wall, if there's some kind of intermittent condition that is going on that is related to some kind of usage condition. So things like vibration and shock, the temperature, thermal cycling, humidity can all affect the part in the field, causing a malfunction or failure that rights itself and the part was working when it comes back. So you're getting a bunch of these things that you're getting these no-fault founds on. You want to develop a methodology of exposing it to various types of environmental stresses like temperature, vibration, or humidity to see if it continues to work under those conditions when you are looking at it in your FA lab for its initial confirmation. Okay, so electrical characterization again of components. Sometimes you're working with a complete module or circuit board assembly, and you got to hunt down what it is, and then eventually you get down. This IC or this resistor or this part is acting up. And if you verify that it is not an issue with the way the part is attached or wired in or whatever connected to the rest of the system, then you usually will detach the part from the circuit board or take it out of the system and start running specific evaluations of electrical performance on whatever that device is. So parametric characterization, measuring its resistances or inductances or whatever. If it's a semiconducting active device, an integrated circuit or a transistor or a diode, you definitely want to put it onto a curve tracer and get its VI curve characteristics. Since those aren't published, it's very, very typical to have a known good part on hand, so you can characterize the known good part for all of its inputs and outputs for VI curves, and then you can go against the questionable part and do the same thing. And when you have a output or an I/O that has a VI curve from the curve tracer that does not match the known good part, then you've got a big clue that this is where something has happened that is where your anomaly is that you need to be reflecting on deeper. There's also time domain reflectology, where you inject a pulse into a device and then monitor what it does on the other end, or if it gives you some kind of bounce back signal. This is again where you need a known good device for comparison purposes, so you can spot any abnormalities or differences from the known good device, and then decide you need to focus further here. And of course, there's all the other standard characterization of inductance, capacitance, resistance meters, lead current testers, oscilloscopes, things of that nature that can be brought to bear here. When you're doing a circuit board, either a bare board or a assembled board, you usually want to be using your in-circuit test, or if you use the flying probe type of techniques for testing, if there's been any kind of disruption in the connections of the circuit board, whether it be a solder joint or a burnout trace or whatever. Now, usually this equipment is set up to be used on your production line. So the failure analysis folks have to negotiate time with the production people, lunch hours or off shifts or whatever, when they can use the equipment for diagnostic capabilities, because very few companies will go to the expense of building these kind of test equipment and having one on the production line and another in the failure analysis lab. And especially if you're using an outside failure analysis lab, they won't have that equipment. You will have to provide that evaluation and include that to them to help them with the testing that they're going to do. And again, if you're not finding anything, adding in some environmental stresses, temperature and humidity, temperature cycling, vibration and shock, just a few good raps every now and then might bring an issue to fruition for you that was there, disappeared, and you're trying to bring it back again. So you can find it and do something about it. Okay, the acoustic microscope is what the medical community calls an ultrasound. We all know how ultrasounds are now being used by doctors to peer inside our bodies or check on unborn infant development and things of that nature. And we can now do the same thing with a sonic picture of an electronic device. We need to submerge the electronic device in a pure water, not tap water, but DI water solution, and we inject a sonic wave into it, and we've got one receiver that's looking for bounce back signals and another that's looking for pass-through signals. And what we're seeing here is what parts of the device are well structured and what parts might be loose or have some form of delamination or voids or air pockets and things of that nature by the way these high frequency sonic signals are absorbed or bounced back. So you can set this with different types of equipment for either high frequency and a short focus or a lower frequency and a longer focus. There's some various setups and recommendations for the various types of electrical components, electronic components that you'll be looking at. I don't want to get into that in detail here. But again, you'll be looking to set these up and get the pulse echo and the through transmission signals and review those side by side to see what it tells you about how structurally intact the device is without having to go to the expense of opening it up and cutting it open. And one of the things we use this for a lot is to find out what part of a device is suspect so we know exactly where to position a cross-section or a decapsulation in order to take away material to see for ourselves with the naked eye what's going on. So here's some examples of the various types of acoustic microscopic images that you get. In this case, the red one that lights up is telling you that there are some voids and air gaps that are going through on this part, or the one that's solid on the phase through is telling you that it's intact, which is why it's transmitting the signal all the way through. So these become a little specialty on how to read and interpret these, similar to how a medical doctor reads an X-ray. And again, here's some more images of how an acoustic microscope can show you if there are areas that are inside that are loose and letting things rattle around. The X-ray microscope is another way to see what's going on without having to go into a physical teardown. Allows you to still keep the device intact for other type of techniques. And we now have very good high-resolution 3D X-rays that allow us to do a lot of angling and viewing and rotating to get a look at the internal structure of the main components without whatever packaging, protective packaging is around them. So we can see if there's any kind of quality issues or failure issues that have popped up inside these things. So you can also do very simple two-dimensional X-rays and look for things like, are all the wire bonds intact, are any of them blown open or detached from either the lead pattern grid or the IC die itself. Another type of imaging technique is infrared imaging, where you can look at your device as it's operating to see the heat picture of what's going on and to look and see if you have any hot spots in the device that are excessive or causing problems. Some other ways we have also looked at things, we said, oh, the device is so close to be off, but here we've got a sneak circuit. This device is still getting a little bit of current through it and it's heating up. Here was another situation here in the lower left-hand corner where we had a circuit board where there was what we called inadvertently designed into it, all these power drivers localized together that created this ring of fire situation. And unfortunately, there was a bunch of aluminum electrolytic capacitors right in the middle of that ring of fire that, and the aluminum electrolytic caps age very, very dramatically at accelerated temperatures. So when we saw this, we knew the caps were rated for the temperature of the application, but then we saw that the power distribution could raise the temperature of the local part of the board another 23 degrees. So we had to go in and increase the ratings on these capacitors to a higher temperature grade in order to endure this and get the same reliability expectations we want to get out of it. Okay, finally the funny sounding thing, SQUID. This is a new technology where it's kind of like your magnetic imaging that is used in hospitals these days. It puts out magnetic fields in order to read the weak magnetic field being produced by current running through various circuits or traces on your circuit board or your components. And so it allows you to see if current is moving in the directions you want. And this is very useful where the currents are so low that they don't generate enough heat to be picked up by the infrared imaging. And here was one very useful thing where we had a conductive filament formation that was inside the board that grew a short between different layers or internal traces of the board. And with the SQUID, we were able to see that current leakage condition where it shouldn't have been, lighting up a part of the board that was supposed to be dark, so we could hunt down that failure mechanism and prove that we had a circuit board that was susceptible to conductive filament formation, which meant we had to go to a better grade of board for this application. So this is this is not widely used yet. These are very sparingly, but they're another new and exciting technique that's out there. X-ray fluorescent analysis. This is using quite often a handheld X-ray gun, which excites elements and gets them to send back a spectrographic pattern that can be used to identify the kind of elements that are in a material. These are being used quite a bit in the European Union now because of the lead-free RoHS, restricted hazardous substances. They can point at a device and quickly see if there are any indications of lead in this device without having to go to other more expensive chemical or spectrographic type techniques. And you can point this, it's point and shoot. You don't have to disrupt anything or do any damage. Now, it's not as accurate as the more sophisticated techniques we'll talk about later, like SEM-EDS, but it gets you in the ballpark to see if there's any traces of concern. Another way it's being used is they're looking at the material characterization of different components, particularly the leads, to see if they match or not. And if they don't match, that's indicating that you possibly have a counterfeit part here that is coming from a non-factory source. So this is a new and interesting tool. So now we're going to go into destructive evaluations, and one of the nastiest is decapsulation. This is where we use some very nasty substances, various acids, to dissolve away the plastic protective casings that go around integrated circuits, so we can expose the integrated circuit, its die and its lead frame, in order to see exactly what's going on, as well as probe it. You know, when you do this, the device still works. You can power it up, and you can use microprobes to read voltages or currents. Later on, you might want to do things like pull testing on the wire bonds to see if they had the proper bond strength, things of that nature. So again, this is not for the weak of heart. These are nasty materials. You need a properly vented system. You need operators, technicians who know how to handle these chemicals without absorbing toxic fumes or burning themselves or splattering, things of that nature. There's a number of different systems for decapsulating different types of components. So you'll want to often use these to directly look at a die, for potential electrical overstress or electrostatic discharge damage, inspection of wire bonds, doing a pull test of wire bonds, like I said, electrical testing, and in a particular counterpart detection to see if the dye is actually the dye that is supposed to be in there instead of a knockoff. Okay, one of the most frequently used techniques is cross-sectioning. And this is where we use a diamond saw and specifically cut into a device at a specific plane and depth, and then polish it up so we get a good, clean surface that we can inspect under a microscope and look for various flaws, such as the oversized void we see in this bulb grid array solder joint here. Now, you can also catch these by X-rays. So very often you'll use an X-ray to figure out where the large voids are in order to then target where you're going to do your cross-sectioning in order to get specific and accurate measurements to see if it is a acceptable size void or an unacceptable size void per the IPC soldering standards. So cross-sectioning can be used in many, many different techniques, from solder analysis to wire bonds to components to circuit board vias, things of that nature. So it is one of the most frequently used techniques, and it does require a high degree of precision because sometimes the structure we're trying to bisect is only 10 or 20 microns in depth. So it's very, very important to get the cut there where you need it, and then polish it to a way that you get the gloss and shine and good, clear, smooth images that you need to see without polishing too much that you grind or polish right through the device you're trying to look at. So there is quite a bit of skill and what I like to call artistry for the folks in our lab who do this. So they do some excellent work for us. And again, there's a whole family of equipment, from the precision cutting saws, various types of polishing, cutting, grinding discs. You mount these in epoxy so that as you're cutting and polishing them, they do not fall apart. And then you're polishing epoxies or polishing compounds, polishing equipment, and the types of microscopes to then inspect them. So it's a bit of a process. You've got to have all this equipment to do it right. Now, very often, once you will get these very, very fine cross sections, maybe optical microscope isn't enough, and you've got to go up to a scanning electron beam microscope, which will take you from a couple hundred X magnification into thousands of X magnifications. And this is what you need to look at these really high density integrated circuit dyes these days. So this is a great tool, but again, you've got to do a destructive sample preparation on it in order to use it. The SEM has a whole series of how it sends different kinds of excitation beams to, one, get the view, as well as what's called a energy dispersion, where you get to excite the electrons of different materials to give out signatures that allow you to do spectroscopy upon it. So SEMs are often coupled with what's called energy dispersive X-ray detectors, spectroscopy devices. So the ion beam excites it, and an X-ray ion beam, and then you have a reader that can read the excitation radiation that's coming off of it, and from that you can identify the elemental content very, very accurately in proportions and area. So this is far more accurate than those handheld fluorescent X-ray devices we talked about a little bit earlier. So one more step above scanning electron microscope is the focused ion beam microscope, which uses gallium ions instead of electrons to put in a finer but more powerful beam that not only allows you to bounce back and see an image, but it allows you to very carefully mill or trench and cut into a specific area of an electronic component, like an integrated circuit die, so you can see below the surface what's going on something that is too small to cross-section and view. And this is a bit of an expensive technique, but sometimes that's what you need to look at a specific electrical overstress or electrostatic discharge or other types of solid-state material structural failures. So let's see here. Oh, we're getting close to the wrap-up here. So now I'm not going to go into great detail on this, but then we have a whole slew of material and chemical characterization tests we can do, from measuring the coefficient of thermal expansion of the different materials in our devices, micro or nano hardness testing to see if they were properly fabricated and are thick enough and hard enough to stand up to our loads, various types of thermal testing, temperature characteristic thermomechanical analysis, differential scanning calorimetry, dynamic mechanical analysis, and there's actually IPC Test Method Handbook 650 has a number of sections. There's actually several hundred evaluation procedures in there for everything from your visual test methods, your dimensional methods, your chemical and material and mechanical and electrical and environmental test methods, all at the various levels of different electronic components and materials that we will rely on as we're doing failure analysis to see if the failure is because the part wasn't fabricated right or strong enough. A chemical analysis technique known as ion chromatography, which is an evaluation method for the ionic cleanliness of circuit board, either raw bare boards or circuit board assemblies. Ionic residues, which come from chlorine, bromide, sulfates, phosphates, nitrates, and weak organic acids that electronic devices are exposed to during the electronic assembly and manufacturing process. If these residues are excessive, they can react with humidity to form an electrolytic solution on the surface of the circuit board that will support electrical current transfer that will drive metal migration, and what you will do is build these dendrite bridges, as they're called, or dendritic growths. They grow from the anode to the cathode until they reach out and touch something and become first a weak and then eventually a strong short circuit between some pads or circuit traces. So this will take out your circuit board and just ruin out your day with some kind of malfunction. And again, there's an IPC Test Method 650 that defines this procedure for measuring these potentially risky residues to make sure in the manufacturing process you want to make sure that you have the appropriate cleanliness level. In a failure analysis environment, we will be looking at these to see which of these compounds is excessive, which will give us an idea of what we have to look for in the manufacturing process to track down its source. So, and this gives you an idea of what these ion chromatography outputs look like, where they give you peaks relative to the degree of contamination found in a circuit board. Okay, and then finally we have Fourier transfer infrared spectroscopy. This is another spectral technique, but this one, instead of looking for elements or ionic, it's looking for organic substances. So this can find organic residues or contaminants on your circuit board. And again, they give us spectral traces that we can read that identify what and the amount that is out there when we're looking for potential failures related to contaminant issues. So that kind of wraps up this brief introduction into some of the most popular failure analysis methods that are out there. And if you'd like to have some more information, we have here some books that you might want to get: Reliability Physics and Engineering, the Electronic Failure Analysis Handbook, Failure Modes and Mechanisms in Electronic Packaging, and the ASM Handbook on Failure Analysis and Failure Prevention Procedures. So with that, I want to thank you all for attending today, and Ed, do we have any questions?
Yeah, I got a couple of questions here, Jim, both of which appear to have, actually here, acoustic microscopy. Can samples that undergo CSAM be used again? In other words, is this a destructive or a non-destructive test?
Actually, if you can fit the entire board in the chamber with the solution, you can actually get the device wet, and we're using a very pure water, DI water in there that doesn't, it's designed not to leave residues. So you can take it out and you can dry it off just like you have power washing in the circuit board assembly, and you can still have that device be usable, yes.
Excellent, excellent. And the other question I have here is that is there another alternative non-destructive technique to analyze BGA solder failures other than CT scans?
Well, actually, there's a new company out here in Michigan that I've been invited to a demo at General Motors on a technique just like that, that I believe uses high-frequency lasers to try and bounce the system out. I'm going to know more about this tomorrow afternoon after a meeting at GM.
Okay.
So maybe hold this person's name, and I'll try and if there's anything good, I'll send them an email with a note.
Sure. I want to assure everybody that everybody who registered and attended will receive a link to the webinar and the recording and the slides as soon as they're posted. One other thing, I've got a question here. Would you clarify the technique for FA of the short circuit? I believe you may be talking about SQUID microscopy.
Oh, in the SQUID? Okay. Well, that is a condition where you'll power the device up and you'll put it in the magnetic imaging chamber. And then you can, either power up everything or you can power up selective circuits one at a time, which actually works a little bit better if you've got a very complex device. And then you can see a pattern that lights up that tells you where the current is flowing, and the intensity of the light up tells you how much current is flowing through there, and because it's reading the magnetic, the very, very minute magnetic signature that's being generated by the current flow.
Okay. Okay. The other question is for the other technique for dendrites in short circuits, ion chromatography. Can we discuss that just a little bit more, Jim?
Okay. Well, in ion chromatography, what they do is they take either an entire board or a section of a board, and they put it in a bag that has a specific solution that is designed to dissolve out the residues and put it in solution. And then they take the solutions and they analyze the solutions for what amount of residue came off of it, and they have to make some very careful measurements on, say, the overall square inches of the surface area of the circuit board. And then they, from reading the amount of milligrams per deciliter in the solution, they can translate that back to milligrams of residues per square inch or per square centimeter, whatever you want to work with on the board. And we have guidelines for what we have found to be acceptable levels of ionic residues, each of the 6 components that we mentioned there, bromines and chlorines and things of that nature, that if you are below these levels, you do not get in trouble in most of your harsh environment, high reliability applications. So things that are out in vehicles or infrastructure equipment out there in telephones or cell phone towers or in military equipment, things of that nature. Now, that's not to say that some consumer product, that is in a much more benign environment could not get away with higher residues because they're not exposed to as much humidity over as much time. But we have developed the IPC test method 650 I referred to tells you how to do the measurement techniques, but it doesn't give you pass-fail criteria. We at DFR Solutions have developed the pass-fail criteria as part of our physics of failure research that we advise our clients on. Anything else? Ed?
I have another question here. What is a recommended test or method to investigate wettability caused by contamination on a component's lead? And I think, we can come at this, I think, one of two ways. Either A, confirming that there is oxidation and quantifying the oxidation on a component's lead, or two, actually just doing some wettability testing. You want to talk about that, Jim?
I think you just covered it very well. Yeah, that's where we can use the spectral analysis to see if we have oxides forming. And of course, under an electron microscope, you can usually see oxidation of various types as well. So does that wrap up our questions, Ed?
So let's take one more question. Can we talk about the decision making, whether, because if you do a dye and pry test, so a dye penetration test, versus a cross section on a VGA, can you just touch on how to come about making that decision, whether you should?
Oh, dye and pry?
Right. When should you use dye and pry versus cross section?
Oh, okay. Okay, yeah, that's a good point. When dye and pry is where you inject a special dye that's very penetrative and goes into any types of very, very small cracks. And then you let it dry, and then you just take a screwdriver or plier and you just pop that device off. And what you do is you're going to break every solder ball, but the solder balls that already had cracks in them are going to have the dye penetration, and you can see the degree of crack penetration in them. Now this is useful for situations where you are seeing, instead of just one part crack, which is usually the corner balls, you are in a very severe situation, or you've got a very severe quality issue that is letting a lot of cracks pop up. Normally you will find your cracks in the corner balls, so you can do a cut on the left and the right, or the top or the bottom, and you get all four corner balls, because the corner balls are the farthest ones away from the neutral axis, so they're the ones getting the most stress in thermal expansion and contraction cycling and in vibration modals, and they're the ones that go first. So usually if you would just do the two cross sections of either side to look at all four corner balls. But if you think you've got another problem, like a quality issue or a severe stress that is putting cracks throughout the array, you would want to use the dye solution and pop it off to see exactly what degree of penetration you're dealing with or degree of defect. Now, one thing you can't do is, if the device is conformally coated or potted, you can't get the dye solution injected in because the potting compound is protecting it. So you can't do a dye and pry in that situation.
All right, Jim. I think that covers it for today. Thank you, everybody, for coming. And like I said before, we will be posting a recording of this presentation online. Everybody will be receiving an email once that occurs, and with a link to the recording. Any additional questions that we didn't get to online, we can provide answers to via email.
I'd also like to remind folks that this was just a very brief introduction of a two-day class we do that discusses failure analysis techniques and the failure mechanisms that are out there, and we will do guidelines on which techniques are most effective hunting down which type of failure mechanism problems. So if anybody's interested in having a class like that taught on site at their organization, let us know and we'd be happy to see what we can work out. So again, thank you all for attending, and for the folks who couldn't get in at this session because we ran out of available lines, there's going to be a second session for the West Coast at 3 p.m. Eastern Time. So if you know anybody you want to recommend to sit in, they can still sign up and join in at 3. With that, thank you all and have a very good day.